All right. Hi, Professor Ramsey. Thank you so much for being here today. Before we
Yeah,
start,
well, thank you for the invitation.
thank you. So before we start, could you briefly introduce yourself, please?
Sure. So my name is Nick Ramsey. I'm a postdoc inside the UCLA Math Department. So I teach math at UCLA, and I study mathematical logic. So actually, I did my PhD in an interdisciplinary program, which had some math and some philosophy in it, although I'm very much a mathematician. And I focus on a part of mathematical logic called model theory, which is like the linguistics of mathematics. It sort of focuses on the way that mathematical words that are expressed in formal languages connect to mathematical structures. And so there's a lot that one can say about that. And that connects to a lot of different areas of math, like combinatorics and algebra. And
Mhm.
that's sort of the corner of mathematics that I like to think about.
Yeah. You said that you have a PhD in mathematical logic, which means that you must have a lot of passion towards this aspect of math. So, what about it fascinate you the most? Why is it this aspect?
Yeah, so when I went to college, I thought I wanted to be a philosophy major.
Mhm.
And
Interesting.
um, I liked math. I enjoyed the experience of taking math, and I took sort of abstract math classes, and I loved working with axioms and sort of doing proofs much more than I liked doing computations. And so
Mhm.
it felt to me like philosophy was a way of spending time in that sort of abstract space without doing a lot of the sort of grungy calculations that I didn't really like. And I took a philosophy class in logic because it was a requirement for the major.
Mhm.
And I loved it. It was just so beautiful to me. And I think if you listen to mathematicians talk about their work, oftentimes they talk about the beauty of the subject and
Mhm.
about how moving it was to them. And I confess that, as hard as I tried as a young person to like feel the magic of the prime numbers or to like feel the magic of plane geometry, it just never seemed to me as obviously interesting as things like truth, justification, language. These kinds of things which are somehow close to human experience and close to things that we as human beings care about. And so when I saw the way that math connected to these things, the way it connected to proof, the way proof could be understood mathematically, the way it connected to language, the way language could be understood mathematically, that moved me, and that really shocked me just how exciting that sort of mathematical grip on these topics was. And I also remember that at the beginning, I had this kind of naive vision that, I could go home and I could translate, um, Shakespeare into logic, and then it would become clear. Like I thought everything would become clear. And what's amazing to me, I mean, what really blew my mind was somehow a lot of people, when they start logic, they have this dream, right? Like everything is going to become clear. I have this sort of language. It's like the language of God. I can finally write everything in its clearest form, and then I will understand. And not only is that not true, but somehow the reasons that that's not true are things that logic explains. Like, can you understand all facts about the natural? Can you understand all mathematical truths? Can we settle all mathematical questions? The answer is no. And the explanation for that comes from mathematical logic. Mathematical logic helps you prove what you can't prove. It helps you explain what you can't explain. It helps you define what you can't define. And for me, that has this kind of sort of topsy-turvy meta feel that was really tantalizing to me as like a young mathematician. And I don't know, I got really hooked and just kept on signing up for more and more classes and more degrees. It turned out that the interesting mathematical logic was in the math department, so that's sort of the direction I went. Although, of course, there's a lot of interesting work done in logic and computer science and philosophy and many other areas as well.
Yeah, definitely. I remember reading this quote by German mathematician George Cantor. I think we learned about him a little bit in discrete math too. And the quote said something like, in mathematics, the art of proposing a question must be held of higher value than solving it. And what you were saying kind of reminded me of that. And I guess I was just curious, what do you think of this quote in general, and how have you seen this quote kind of playing out in your own pursuit of mathematics?
Yeah, I think the idea there is that you know, you can pose questions that are somehow in a familiar vocabulary, and then that suggests to you that you should solve them using the methods that you know. But if you can ask a question that somehow puts a new perspective on a mathematical topic, or makes you see it from a totally different point of view, then that somehow can knock you off kilter and bring new things into view that were not there before. So for example, Cantor himself, one of his principal contributions was to give us infinity in a way. You know, like before Cantor, I think the concept of cardinals and ordinals was not nearly as well understood. And, you know, he introduced infinities and explain to us, prove to us that there's more than one. You know, so we know a lot of infinite sets, we interact with them. So we have like the natural numbers or the even natural numbers, the rationals.
Mhm.
And then we have sets like the reals and sets like the complex numbers. And I think intuitively we grow up thinking about these as all being infinity. You know, they're all the same size. But what he proved, which you know, it's still a really beautiful fact to me, is that, you know, the size of the real numbers is bigger than the size of the natural numbers. There are more of them. And then you can form sets that are even bigger than the real numbers and even bigger than that. And in fact, there is not just more than one kind of infinity, but there are infinitely many infinities. And there's so many infinities that you can't assign size to how many infinities there are. And okay, at one level, this is just talking. You know, like I can just say stuff about infinity in the way that poets say just things about infinity. But what he did is he sort of gave us a notion of infinity that was really rich and meaningful, and he just sort of opened up, you know, a kind of paradise. People refer to it as Cantor's paradise, right? Because um, in some sense, it's mathematics that any child would love. You know, what is the sum of two infinite cardinals? It's the max of the two. What is the product of two infinite cardinals? It's the max of the two. Any grade school child would love that kind of arithmetic. But when you reflect on it long enough, you start to understand the real richness that he discovered. And it all came from asking the right question, which is, how do I continue after the natural numbers? How do I keep going after I've exhausted all of the finite steps? And reflecting on that kind of infinity was a really profound move. And yeah, I mean, I think there are places in mathematics where you see that the advance didn't come from some kind of technical uh, tinkering. It really came from asking a better question. And you know, we all hope that lightning strikes and we get these kinds of conceptual uh, glimpses. Sometimes it happens, but most of the time it doesn't.
Yeah, definitely. So it's not always about, just like solving things, but more about, thinking about how questions can be asked that lead to a better understanding of something. Would you say that that's the case?
Yeah, 100%.
Yeah.
100%. Basically, you know, you get this picture when you grow up doing math classes. You take an algebra class and you find the roots of a bunch of quadratic polynomials. You take a trig class and you take sine and cosine of a bunch of angles. You take a calculus class and you compute long lists of integrals. And basically the methods that you learn to do this are methods that have been well understood for a very long time. But now you imagine that you're going to try and do mathematical research. And now you're confronted with a question that no one has solved before, but also like the methods maybe don't exist. So you have to think about, okay, what are the resources that I'm going to marshal in order to understand this question? How am I going to form analogies with other things that are there? How am I going to somehow put some kind of conceptual grip on this thing that seems really mysterious? And sometimes that's merely a matter of tinkering. I mean, that does happen, but oftentimes it's a matter of asking what new concepts are going to give me, or are going to let me sort of cut this problem by its joints. And that's a very creative and not at all straightforward kind of endeavor. It's very different than finding the roots of a quadratic polynomial or computing a definite integral.
Yeah, for sure. And I was just thinking it's interesting how, like, growing up, I feel a lot of the math classes that, like, at least for me, like, I've taken, in them I was taught, to like always to just solve things and compute things, but there's actually like a whole spectrum of, like creativity and this more like this thing that requires more reflection rather than just like brute force computing
Yeah,
math.
yeah. Although I should say that brute force has its virtues. You know, like when I was in elementary school,
Mhm.
uh, I remember very distinctly, like at some point we had to learn our multiplication tables. You know, you just
Yeah.
have to learn from memory, what is 3 times 5? 15, okay? What is 6 times 7? 42, okay? And you have to be able to write this down very quickly, and you have these timed tests.
Right.
And I remember, when we learned multiplication, what are you told 3 times 6 is? Well, you're told that you add 3 plus 3 plus 3 plus 3 plus 3 plus 3. You add 3 to itself 6 times, and then you add it up, and then you get, okay, 18. And so you have a kind of algorithm for figuring out multiplications. You can sit there and, whenever you see 3 times 6, you can add 3 to itself 6 times and then see what you get. So if you understand addition, then why do you need to learn multiplication? And I remember like crying in the 3rd grade, like, why are they making me do this? Because I can answer any multiplication if they just let me add the numbers long enough.
Right.
And they were right that that drilling was important, because later on when you're computing exponentials, later on when you're trying to find roots of quadratic equations, later on when you're writing your thesis in the math department somewhere, you need to be able to multiply numbers, and you don't really want to sit down and have to think about all the steps, because that forces your mind to focus on that, and then you can't make the leaps that you need to do in order to see sort of how the concepts fit together. So there is a lot of drudge work. There's a lot of technical drilling, and that's miserable. But it's sort of like lifting weights if you want to be a power lifter or something. It's just the exercise that you have to do to get there.
Yeah.
So I don't want to say that like all the interesting mathematics happens at this conceptual realm, which is really far away from the concrete details. In some sense, the beauty comes from like the accumulated effect of a lot of small
Yeah.
details.
It's like
But there's an
foundation.
interaction between these two levels.
Mhm. Yeah, that's really I like that analogy a lot. Kind of like describing the connection between the computing and the, I don't know, the more reflective side of math. So I guess my next question is, during the course of your study, whether it's for undergrad or PhD, um, was there ever a time when you felt overwhelmed or that you were kind of just hitting a roadblock in terms of your academics? And if so, like, how did you overcome that?
Yeah. Well, I think the better question is, was there a time that I didn't feel that way? You know,
Yeah.
I remember it was like my 3rd year of college. After that year, there was an REU. So this is research experience for undergrads. So it was a program at my school where um, all of the math undergrads that wanted to basically got to stick around over the summer, and they wrote some expository paper about something, and there were lectures given by different professors. And I remember one professor just saying, most mathematicians spend 99% of their time feeling completely and horribly confused. And they feel somehow inadequate to the questions that they have to consider. And they feel like they have no idea where the next progress is going to come from. And it was really a revelation to me to hear that, because, if you're sitting in a classroom and the professor asks a question, and there's some person sitting in the corner of the room that just gives the answer, uh, and the answer didn't just occur to you. It's very hard not to feel inadequate about that, right? I mean, you think, okay, well, something was clear to them and it wasn't clear to me. Why? And and then maybe that keeps happening, right? That person keeps answering the questions and it's not coming to you.
Yeah.
And that then you think, okay, maybe they have something that I don't have. Maybe they're a math person. I'm not a math person. But okay, there are just a million variables that can explain why that person is answering the question and you aren't. Maybe they've thought about this subject before and it's new to you. Maybe they have really rich parents who are paying for tutors and you aren't. Maybe they are really talented, and maybe you are a kind of person that has to do math in a quiet, isolated space in order for things to click. There are lots of explanations, and all of these are legitimate. But math does not happen fast. Math sometimes happens in competitive settings, like the IMO exam. But the math that really contributes to the world is the math that happens, when people are working, and that doesn't necessarily happen at a really quick pace. So, I think it was revelatory for me to understand that people are really confused all the time and they have no idea what's going on. People go to mathematical talks and they sit in the audience and they have no clue what is happening. And they find sometimes even the words don't seem familiar to them, and that feeling is normal, and encouraged, you know? So there's nothing wrong with not understanding. And in fact, it's oftentimes very useful to put yourself in these situations where you feel sort of at sea, because then, you know, you sort of force yourself to learn if you stick with something comfortable the whole time. But that feeling at sea is intolerable if you think that it's somehow unique to you, right? If you think that I'm at sea, but all of these other people feel comfortable, or I'm completely lost, but all of these other people get it, or I'm somehow way behind, I can't possibly get past this. And um, I don't necessarily know how to communicate to people just how pervasive this feeling is to everyone at any level.
Yeah.
But I do really think that, like, if there is an enemy to, you know, like, you know, math is a general, you know, it's a generally collaborative enterprise. We try to build, we don't attack things. But if there is an enemy of mathematics, it is this idea that there are math people, that there are people that just get it, that there are people for whom math comes very easily. And I don't mean to deny that, I mean, okay, there are differences, of course. You know, some people learn languages very quickly, some people it takes a long time. But math is accessible to anyone. And the idea that to enable, you know, to be able to meaningfully do mathematics, you have to be able to do it quickly, and it needs to come somehow naturally, is just one that you know, that's there's no worse idea. You know, it just has to be banished. And so I think it took me a really long time to come to understand that, you know, I could contribute to mathematics. You know, I came to math a little late. I wanted to study philosophy at the beginning, and so I thought maybe I'm just too far behind when I started. Then, you know, I went to grad school, and suddenly I was surrounded by these people that were really good, you know, just really intimidatingly smart. And it felt really, you know, hard to understand how I might be able to make a contribution. And these were just my grad school colleagues. I mean, if you look at the profession, you look at the depth of mathematical talent, and achievement, it's really shocking. So it took a very long time to understand, okay, anyone, literally anyone can contribute to mathematics in some way. Literally anyone can do mathematical research of some form. And I'm not saying that every person is going to get tenure at Harvard. Not every person is going to become a professional mathematician, and that's fine. But, you know, math is part of the world in which we live, and a lot of people can find ways of meaningfully engaging with that, in the same way that anyone can play soccer, even though not everyone has to. Well, not anyone can play soccer, but many people can play soccer, even those who are not going to become professional soccer players. So uh, I think, you know, this democratic impulse for mathematics as a kind of activity for everyone is one that I
Mhm.
didn't see at the beginning, but one which I think is a really important component of what makes it a meaningful thing to do.
Yeah, definitely. And I relate so much to the feeling of like panicking when I felt like everyone around me is getting something that I'm not getting. And I think I don't know, it's really important to know that just being in the process and making effort is it's more important and better than just getting it all the time. And besides just getting it quickly, that's not really a thing. It's kind of like a myth. So I felt it's very encouraging to hear that from you. And kind of speaking of this like math being a thing, being a part of people's life, I felt that some people might have this struggle to find a connection between math and their own life, where they kind of treat math as this irrelevant, theory heavy, isolated subject to study for. How can people that have this struggle see math under a different light in order to enjoy learning it a bit better?
Yeah. Well, it's a good question. You know, I think people have different views about what makes math appealing to people. And I remember when I was in college, for example, I think just about everyone was required to take some math class. And, you know, there were three different calculus classes, for example. I mean, one was honors calculus, and then sort of like mid-level calculus, and then there was one which was geared for people that were not going to go into fields that were necessarily quantitative. So people that, you know, wanted to study English or something, they had to take some math, but maybe they would take this one. Then there was this other option, which was like number theory. And most people that had to take a math class opted to take the lowest level of the calculus class unless they had some reason to do something quantitative. That was supposed to be the one that was like closest to lived experience. You know, you solve word problems. There is, you know, a hose that's filling up a pool at a certain rate, and then, you know, how does the volume change, so on and so forth. So this one looked more applied. It looked more relevant to people's lives because it, you know, there were word problems. But these word problems were not really word problems, right? They were calculus problems that had, you know,
Words.
sort of silly real word vocabulary stuck in them.
Yeah.
But many people I knew, people that, you know, wanted to study English and were interested in poetry, people that wanted to study history, whatever, they took the number theory class and without fail, they all loved it. And part of the reason why is because you start to just have this experience where you're confronted with something that seems abstract and really, really so conceptual and so pure that it seems like it's some kind of frictionless space in which you can't imagine making meaningful conclusions. But then you learn some techniques, you learn some ideas about, say, modular arithmetic and how to think about that. You learn some things about, I don't know, rings, some things about various different kinds of algebra, like the Chinese remainder theorem. And then suddenly you have these new tools. And seeing that kind of conceptual development, seeing the way that like sort of quiet reflection on abstract things can lead to surprising conclusions that you didn't anticipate, using logic to write compelling logical arguments and proofs. Um, you know, that seems like something that's supposed to be very advanced, but in fact, anyone can do it. And I think many people for whom the sort of calculating, computing, calculus-like aspects of math doesn't has no appeal, those people without fail tend to really, you know, vibe with this kind of conceptual
Mhm.
mathematics. And I mean, there's something really beautiful and striking about just this idea that, you know, these prime numbers are there and, you know, there are facts about them that you can discover and you can write proofs that uh, tell you things that you just couldn't have guessed. And so, you know, the question is an interesting one. How can we make people feel like math is relevant to them? You
Mhm.
know, y- you could ask similar questions about like novels, right? So
That's
some novels feel interesting to us because they describe characters that we can identify with, right? We can look it and we see, okay, this character has gone through experiences like me and identify with that. But other times we read novels that are about people that are in very different contexts, that have totally different experiences from us. And nonetheless, their stories can be really compelling and we can learn from them. And I
yeah.
think math is the same way. Sometimes math is compelling because we see problems solved that look like problems that we had to confront, and we're happy that we have tools to solve them now. But other times we just enjoy the trip to some kind of interesting conceptual realm that we hadn't wanted to visit before. And for me, it's that kind of latter kind of mathematics that I think uh, sort of underutilized pedagogically. I mean, I think people like to go to that space. People often find it beautiful and interesting and
Mm.
intriguing. And I think there's a lot of mathematics that happens at this kind of abstract, uh, far from lived experience realm. And I think that often is something that we can focus more on.
Yeah, definitely. I love that perspective. And I think it definitely offers good insight and um, good answers to people who have questions about why they should study math, even though they're not gonna, even if they're not gonna pursue it in the future. But yeah, that's that's a really great answer. Um, and I guess as we um, wrap up a conversation, there was one um, one last question that I wanted to ask. So this is more in the like the education side, I guess. So we've been in this Zoom university situation for over a year now, and at least from what I've seen, from what I've heard, there's just a lot of fatigue over learning via Zoom and I think just frustration over online learning in general. And my question is, how do you think this has taken a toll on the students in terms of their mindset and motivation for their education? And what do you think can be done to help students kind of gain back that momentum and improve their learning experience when we come back together at school, return to campus? hello?
Okay, I think the connection dropped out there for a second. I'm sorry about that.
Oh, no.
Okay, but now it's good, I think. Um,
Should
so anyway,
I
sorry,
repeat the question? Did that get cut off
I
or
think I got it, right. So students have been going through COVID for like a year now,
right?
and you know, uh, I think teaching is not the best this way, but I think being
Yeah,
a student is just the worst. I mean, I can't imagine being in college during this. So, like my heart breaks for the students that lost a whole year of college. College is like a really special time, and uh, I think that it was just a pale comparison to what it could have been like otherwise. So I think uh, we understand now in ways that we perhaps didn't, the value of human contact. Being able to be in um, an office or in a classroom and be there together, um, to be able to interact with the professor. Like when I teach in a classroom, I can look out in the classroom and see what people's faces look like. You can look and see, okay, are people looking confused? Are people looking happy? Are people looking bored? And adjust accordingly. And on Zoom, most of the time people
don't have their
don't have
camera.
cameras on at the very least. And there are things that you can do to try to take the temperature, right? I mean, you can have a poll, you can have the chat open and talk, but it's not the same.
Right.
And um, I think office hours, for example, I remember, when I was at UCLA in my first year, sometimes people would come to my office and we could actually work at something together on the board. And that kind of togetherness is really hard to replicate over Zoom.
Mm.
So I think at this moment, we are all sort of reflecting on what the past year meant and how we can somehow bounce back from it and feel like it wasn't a complete waste. Clearly, some things about the way this past year went were good, right? I mean, I think the idea of recording the lectures and making them available, having the notes always available, that was probably useful for many
Yeah.
people. Having some flexibility about like when quizzes can be done, I think that was probably nice. But it does seem like the classroom experience is a kind of pale substitute for being there together. And um, so rather than reflect on how one can make COVID more bearable, I think I would prefer just to say, I think there are a lot of nice lessons that we can take going forward about what it was about having this kind of flexibility, geographic flexibility, time flexibility, of interacting with each other online. But at the same time, remember that like we're not going to be doing that next year. That's going to be the best feeling ever, I think. God willing. So obviously it's far from clear, but it looks encouraging. So I'm going to try to be optimistic and hope that all of us can have a nice university experience next year.
Yeah, definitely. With this like past year's experience of teaching online, do you think that if and when we return back to in-person classes, do you think that um how do you think you'll construct your class? Would it be different from how you've done it before COVID started?
Well, so, for example, I think some things I mean, I think having submission of homework, for example, online, having even the quizzes being done online, sometimes worked pretty well, because it takes up less time. It's very easy for people who aren't physically present. Like if you're going to be out of town on the day that homework is turned in, maybe it's better just to be able to do it this way. I think these things are quite convenient.
Mhm.
Um, I also I think we'll probably be open to meeting with students on the internet, even if normally office hours will take place in person. Because I think it's just kind of a standard thing now, right? Like if a student is out of town for some reason, or I'm out of town for some reason, meetings can happen that way, and I think that kind of flexibility is really useful.
Yeah, definitely.
But um, actually, in a way, for me, what was most interesting is just how um, nice in retrospect the traditional classroom lecture seems, right? So
I miss that.
yeah, I think a lot of that. we'll just go back to normal because, you know, if it ain't broke, don't fix it. I think having like a lecture where you can engage with the students and have a board in front of you and having office hours in particular, I think really suffered under the Zoom model. So I think going back to the parts of that worked really well is something that I'm looking
Mhm.
forward to.
Yeah, definitely. Well, thank you so much for,
Yeah,
I feel that was a great, um, like, there was a lot of insight that offered that really, um, gave me a different perspective on, learning math and just learning in general, and I, really appreciated your time and everything. So thank you.
yeah. Well, thank you. So, you know, like I get to talk about math a lot, but normally it's about, you know, like what is 6 choose 3 or something. So it's sort of nice to be able to talk about sort of like what it all means, and why it's interesting.
Yeah, definitely. Um, well, okay, I'll stop the recording now.